I hope it is. Okay, so hello everyone. Let me welcome you to FOSDEM and to our virtualization and infrastructure as a service dev room. And I'm the first speaker of the day. And in my presentation, I'm going to talk about how you can run Windows guests on KVM efficiently. So in your infrastructure, you're running virtual machines. And some of these virtual machines are Linux VMs. Some of them are probably Windows VMs. So does it make any difference from the virtualization tool stack point of view, like which operating system you are running in your guest? And the answer, well, it depends. So in theory, it doesn't, because with QEMU and KVM, we are actually trying to emulate some existing physical hardware by building a virtual machine, right? But then, if you boot your Linux guest on KVM and take a look in the log, you will see something like this, right? And you will realize that your guest knows pretty much everything about the fact that it's running virtualized. It knows that it's running on KVM, and it's actually using some features. So why do we do that? Well, the thing is that when we are trying to emulate physical hardware in software, that some interfaces were not designed for that, and it can actually be slow in some cases. So how do we solve these problems usually? Well, if the hardware interface we need to emulate is slow and we cannot make it fast, we come up with our own solution, and we invent so-called paravirtualized interface, which is fast and which is software friendly, right? But then when we have our own interface, we have to put support for this interface in the guest operating system, right? Because it doesn't know anything about it. But the question is, what do we do about proprietary operating systems like Windows? How do we put these interfaces there, right? We don't have the source code. And, well, we can probably try writing drivers. And that's actually what we do, for example, with VirtIO devices, right? But the thing is that not everything is a device from Windows point of view. And some very core features of it, like interrupt handling or clock source, are actually not devices, not drivers. They're in the core of the operating system. So you may have hard times writing these drivers for your proprietary operating systems. And moreover, there are multiple different Windows versions, and you'll basically have to check that this solution works for every of these. So what else can we do? Well, we know that KVM is not the only hypervisor out there. There are other proprietary hypervisors, and the thing is that these hypervisors have to solve the exact same issues because, well, for them, these hardware interfaces are also slow, and they also have to come up with their own interface. So in Windows world, this hypervisor is called Hyper V. And we do emulate Hyper V in both KVM and QEMU. And there are basically two different types of emulation there. We emulate these core features, which in Hyper V world are called enlightenments, and that's why my talk is called Enlightening Hyper V. I'm going to talk about the first part. Device drivers is something which would make it possible to replace, for example, VirtIO. So if we write VMBus device drivers, then we won't need VirtIO drivers for Windows. And there is such effort, and Virtuoso company is currently working on it, but it's not currently upstream, and I'm not going to talk much about it in my presentation. So Hyper V features which we emulate. Where can you read some documentation about them? There is no in QEMU and KVM for you as a user. And in libvirt, you get this. That's basically it. Probably not much. You may or may not understand what these features are. And if you want to know more, you can go and basically read the specification. Hyper-V folks were generous enough to publish their spec. It's there on Microsoft website. Or you can listen to me now. So what features do we have in KVM, and what are they needed for? So I'll be showing you both QEMU syntax and libvirt syntax, how you can enable the feature, and I'll tell you a few words what this feature does. So let's start with this one. It's called like relaxed timing. It's enabled by like HV relaxed in QEMU and like these features Hyper V, something in libvirt, and mostly these Hyper V enlightenments in libvirt are enabled like that in features, but there are some notable exceptions. I will show you them. And this feature basically tells your Windows that it's running virtualized, so it should disable all hard watchdogs on different events, because different operations can take different time when you're running virtualized, right? So if you put some hard watchdog there, your Windows can crash. And actually more than Windows versions, they don't require these. They will detect hypervisor CPU flag and enable this automatically. But for older Windows versions, it makes sense to enable it. Paravirtualized Epic. So it's enabled by HV Epic. And it basically provides a shared page for each CPU to assist dealing with Epic. And the notable feature here is paravirtualized end of interrupt. So here is a good example when like emulating hardware interface is slow. When you have an interrupt, right, and like a level triggered interrupt pending, your hypervisor will stop your guest, inject the interrupt there, and resume your guest. Your guest will notice the interrupt and probably will start doing something about it, like launch like an interrupt service routine. But when it's done, it needs to somehow signal the fact that it's done with the interrupt and it's ready to receive the next one, right? And in hardware, like in physical Epic, you basically write to a register. And the operation is like pretty fast, right? So you write to the register, it resets the bit, and then you can receive a next interrupt. But if you do it under the hypervisor, you will get a VM exit, right? So your guest will be stopped, you will drop in the hypervisor, and hypervisor will basically mark that the interrupt is not pending anymore and resume your guest. It takes time. So so-called PV end of interrupt was invented. It's basically like the guest is just clearing one bit in the shared page, and the hypervisor will periodically look at this bit, and when it's not pending anymore, we are ready to inject next interrupt. We don't need to do it synchronously most of the time. And there is a side effect that this feature is also required for Enlightened VMCS feature. I will tell you about this feature later. Paravirtualized spin locks enabled by HV spin locks, and you can tell it like QEMU how many attempts to do before like giving up. The thing is, like, there is a core concept of a spin lock, right? When two CPUs are trying to get the same resource, they may do this like cheapest possible lock-in. It's basically like checking a variable in memory and seeing if somebody else is doing something with the shared resource, and you set like basically one there, you do something, you reset it, right? The other CPU looks at it, oh, it's busy by someone else is doing the job, and it just spins. It doesn't do anything. It constantly checks the state of this indicator to see if it can do something. In the virtualized world, it can take significantly longer because your virtual CPU, which actually took the resource, may not be running at this moment, right? It can happen that it took the resource and then it was offloaded, right? And some other guest is running there. So your CPU, which is trying to get the lock, will have to wait for quite some time. Instead, we can basically give up and give a chance for other vCPUs or other guests on the same physical CPUs to run, right? And that's what the feature does. We also have a counterpart in KVM, but Windows cannot use this KVM feature, so we can enable this Hyper V feature. Next one is a simple one. It's like VP, Virtual Processor Index. It basically creates a virtual model-specific register where each CPU can read its own number. And in QEMU, they almost always match like the order in which they were created. CPU 1 will get 1, CPU 2 will get 2. But the thing is that we need this model-specific register for some features I'm going to tell you about. And Windows, if it won't see this feature, it won't use this PV-TLB flush and PV IPIs, for example, because in these hypercalls, CPUs are actually specified in these VP index terms. Runtime information, right? So you have a virtual CPU, and sometimes it runs, sometimes it doesn't, and some other virtual CPU or the host is doing something on this physical CPU. And if you want to do some like fair scheduling, for example, you may want to give your tasks same slices of time to run. But the thing is, you think that your task is running, but actually it's not. And something else is running there. And how can you know that, right? So there's a protocol, basically, again, like a shared, like a register, model-specific register, where Windows can read the information for how long the vCPU was running and for how long something else was running there. But the thing is, how it's done in Hyper V, it's done through a model-specific register. It's not a shared memory page. So reading it will trap in the hypervisor. So it's kind of slow. And Windows, as far as I know, doesn't do that for scheduling by default, because it would be really slow to switch between tasks. And I'm not exactly sure when it actually does use the feature, but maybe sometimes it does. Crash information, that's quite interesting. So your Windows crashes. Everybody knows that, right? So you will get a blue screen of death. But the thing is that not all of them are the same, right? So you may want to know, especially if you're running VMs on a larger scale, you may want to know, like, if you're actually seeing same crashes on like different hosts, or these are like different crashes, or like how many different crashes do you have, so you can analyze them. And Windows can provide some information, basically like 5 registers, or I don't know, yeah, I think it's 5, on crash. And you can get this information. If you enable the feature, then in libvirt log, if you're running through libvirt, in QEMU you can get this information too, but I think you need to do like a QMP command, so it's not easy to get to this information. From libvirt, you will get it by default in the log, I think. Windows will tell you basically where it crashed and some parameters like registers. So by comparing these in the logs, you can see like if you're seeing same crashes or different crashes. It can come handy in some situations. Clock source. It's actually one of the most important enlightenments, and the thing is that in some workloads we need to get timestamps pretty frequently. You know, for example, we are trying to timestamp records in the database or network packets. So your operating system will constantly be reading from the clock source it has, right? But the thing is, what is the clock source it's trying to access? And on physical hardware, it's usually, nowadays, it's TSC. It's a register in your CPU, which is usually good. But in virtualized environment, you cannot do that, because your VM can actually, for example, migrate, and there's going to be like a jump in TSC value, and the jump can actually be backwards, so not nice. And virtual machines came with this concept of a virtualized clock source. And in KVM world, it's called KVM clock, but Windows is not going to use your KVM clock, right, by itself. So we emulate Hyper V clock, which is basically the same concept. It's a shared memory page with 2 values, and to get the timestamp, it reads the TSC register from processor, multiply by like scale, and add the offset. If your VM migrates, hypervisor will update these values, and the reading will stay like persistent, so it won't jump anywhere. So it's quite useful, and it speeds up Windows a lot. So if I will have some time, I will show you some benchmark at the very end of the talk. So synthetic interrupt controller. So that's the core component of building VM bus. VM bus is the key component how you can create these PV devices, which I'm not going to talk about, but that's how you can create PV devices in Hyper V. So it allows you basically to, it's something like a communication protocol between the guest and the host. You can like both basically post messages and signal events. And it's not interesting by itself unless you have some VM bus devices which are not yet implemented. But this enlightenment is required for Windows to use synthetic timers. And synthetic timers, synthetic timers is something like an alarm clock, right? You want to get an event in like 1 second, say, right? So you set a timer, you get an event. And Windows does this pretty frequently. So again, in hardware world, you can use something like TSC deadline timer now, right? So you set next TSC value and you will get an interrupt when it happens. It's going to be quite slow because you will have to program this every time there is an event. And again, it means that you will be exiting to the hypervisor for each event. You can set a periodic timer with this enlightenment. And actually, there was an update of Windows 10 and Windows 2016 last year when they changed the frequency of basically setting up these timers. And there was like a huge performance regression for Windows guests under KVM. Users were seeing their guests constantly spinning, like consuming 30% of the CPU even when they're idle. You enable this and this goes away because Windows sets this timer once and gets this event when it needs it without any hassle. TLB shutdown. Again, as you know, like when you map something in memory, you may want to flash a TLB buffer, which is like a fast translation from one to another, from virtual to physical. And in x86 world, if you want to flash this buffer on other CPUs, you send APIs there. So it's basically interrupts, and you wait for them to perform just the shutdown. In virtualized world, it may happen that these virtual CPUs you want to flash are not actually running. So it's kind of pointless to flash buffer there in the first place. And second, you will spend quite some time waiting for this to happen. So they came up with this concept of virtualized shutdown. So you tell the hypervisor to do the shutdown operation on your behalf. And hypervisor actually knows which vCPUs it needs to flash and which are not running, and they don't require flashing. So this speeds up some overcommitted environments significantly when you have like more virtual CPUs than your physical CPUs. Pretty similar concept with para-virtualized APIs, but it cannot just like drop the API because this interprocessor interrupt, they have to happen. The only thing that we can send APIs to, for example, more than 64 CPUs at a time with this. And in hardware, you'll have to do a VM exit for every 64 CPUs you want to send. So it becomes like cheaper. Yeah, there are a couple of like useless things you can do. Like you can set Hyper-V vendor ID. Microsoft Windows doesn't care about what you put there. You can put like Hyper-V, KVM, Microsoft, Hyper-V, it doesn't really matter. The other one is para-virtualized reset. So another model-specific register which allows your guest to reset itself. And the thing is that even genuine Hyper-V doesn't recommend using it. So the feature is there, but for no particular reason at this moment. But maybe for some very old Windows guests, it was required. For modern guests, it's not required. So there are also a couple of features which are required if you are running nested guests. If you're running like Hyper-V on KVM, or if you're enabling some security features in Windows which actually enable Hyper-V underneath, there are such features there. And first is, if you want to get stable clock source, and I just told you how important it is to have a stable clock source, if you're running nested, you will need a couple of additional enlightenments. One of them tells your level 1 hypervisor about your epoch frequency. The other one tells it when it changes. For example, when you migrate your level 1 guest with all its guests somewhere else. So it actually needs to know that the frequency changed. And that's how you do that. It's not currently fully supported in KVM, so actually it doesn't send these re-enlightenment events. So if your CPU is more than enough and you have TSC scaling, it's not an issue. But if you're running on older CPUs, your clock may start ticking at the wrong frequency. It can happen, so we know about it. Enlightened VMCS, I was telling, giving a talk about it like last year. It's like pretty complex feature, but the thing is that to run virtualized guests, you're dealing with such called VMCS state on Intel, and you're using specific CPU commands, specific instructions, which are first not very fast, and second, I mean, if your level 1 guest is building this state for its level 2 guest, you don't know what it's actually doing there because it runs on the CPU natively, so you'll basically have to read the whole state. There is a PV protocol for that which speeds things up for that. So we have more features in works, and this one is already on the mailing list, and that's why I put it on the slides. If you are running Hyper-V on KVM, it would also like to see synthetic timers there, but it cannot use synthetic timers in their current shape, in the shape in which Windows uses them. So, because it doesn't set up like full this infrastructure, the Hyper-V is like a very minimal hypervisor there. It wants like a simplified mode, and a simplified mode is getting an interrupt instead of a VM bus message. And for that, there is this timer direct enlightenment, which is already implemented in KVM and which will land in QEMU shortly, I believe. As I promised, some benchmarks so you understand how important these enlightenments are. So, this is Hyper-V clock source. What we do in the test, we basically spin and we do clock get time. It's like basically what's the time right now, right? In the operating system. So if you run it with and without HV time, you will see the tremendous difference because with HV time, it's basically reading from memory. So it's not very different from actually like reading like TC register from processor on bare hardware. Without HV time, it means VM exit to the hypervisor every time. So the speed up is great here. Enlightened VMCS. If you're running nested guest, and you will do some operation which actually traps in the hypervisor, and CPU ID is, as you know, like gives you this like CPU features you have, but it always needs to trap in the hypervisor. So you will see that with HV VMCS we achieve like 10% difference here. With TLB shutdown, the test case is quite complex here, and this one is like part of it. But the thing is, we are doing mmap and munmap of some like big file in chunks, and this operation is known to cause TLB flushes on other CPUs. And then what we do, we are running the same test on the same host, but we are just adding more and more virtual CPUs to our guest. And as you can see, when the number of like virtual CPUs matches, there is almost no benefit in the feature. It's the same, right, as sending these APIs and doing flash natively. But as we go over committed, like more and more CPUs we have, this PV-TLB flash on the right, the number stays more or less the same, because we don't really need to flash these vCPUs which are not running, and they cannot be running at the same time. But with physical PV-TLB flash, you will see the slowdown of the same test case on the same physical host. That was it from me. Thank you for listening. Any questions? Yes?
Just regarding the features you mentioned, on which versions we can expect to have them and to make use of them?
The question is on which versions we expect to see these features. I'm guessing that you're asking about both like KVM versions and QEMU versions. Yeah, right. So everything I was telling you about today is already upstream in KVM, including the synthetic timers direct mode. In QEMU, I don't actually remember like off the top of my head, but I think that everything except for like PV, TLB flash, PV IPI, and Enlightenment VMCS is there in like 2.12 or something. In 3.0 we were adding like PV TLB flash and Enlightened VMCS, something like that. So if you grab current QEMU, it has everything but this synthetic timer direct mode. The RFC is on the mailing list. I'm also trying to come up with a simplification which would be called like HV all, which will enable all Hyper-V features for you. It's like a little bit controversial because the question is what happens when you migrate such a VM, right? Your other host may have different Hyper-V enlightenment support, like you have different KVM versions. So like libvirt folks prefer to have all these enlightenments listed there, so prefer to keep them like fine-grained. And they may not support it, but in QEMU it may actually come handy for like development test cases for a single host usages, stuff like that. So expect to see this feature in near future. More questions? Yes. Oh, so many. At the back, you were the first to raise your hand, so please go ahead.
What's the cost of enabling those hyper-enlightenments for the gas systems that you know about them? Basically, why are not they enabled all by default?
Yeah, the question is why are these features not enabled by default, and what's the cost for enabling them for the guest operating system? The cost is basically zero, except the notable exception is Enlightened VMCS, because Enlightened VMCS comes with a penalty. For example, you will have your post-interrupts disabled. And for some workloads, when you have, for example, some physical hardware which is actually able to deliver post-interrupts, that's going to be a slowdown. In other cases, when you don't have such hardware, it will be a speed up. So this feature we cannot enable by default. The rest, the cost is zero, even if your guest operating system is not using them. You can enable them for your KVM guest and you won't notice anything. Why we don't enable them by default? Probably because of how the virtualization stack is designed, and the most important thing there is migration, right? So if you don't need these features, but you enable all them, that later you cannot migrate this VM to some host which doesn't have this feature. Because from the hypervisor point of view, we don't know if the guest is using the feature or not. Or we will have to come up with an interface. Oh, was the guest using this feature or not? Can we disable it? We don't have this in either QEMU or KVM. So yeah, so thank you guys very much. We're out of time. So I will take your questions here in the corridor. Yes.